In this segment, we will go through a quite representative application of the Bayes rule to a situation that involves two continuous random variables. The setting is as follows. We start with two independent random variables, and we get to observe the sum of the two. So, for example, we might have a signal. That signal is transmitted through some medium, and so it is corrupted by noise, called the noise y, and we get to observe z. On the basis of the observed value of z, we would like to say as much as we can about the unknown signal x. How do we approach this? Well, we will try to find the conditional distribution of x given the value z of the signal that we have observed. How do we calculate this conditional distribution? The setting here suggests that we should be using the Bayes rule. So let us write down the formula for the Bayes rule that we already have. On the other hand, this formula does not quite fit the setting here. This is the formula that would be applicable if we were to observe y and try to say something about x. But here we are observing z, we're not observing y. What should we do? It's very simple. Just use the same formula, but instead of having y's, use z's. So the formula takes this equivalent form. So this is what we want to calculate. The conditional distribution of x given an observed value of z. In general, we will be given the distribution of x, so this will be a known quantity. But how about this? We need the conditional distribution of z given x. In other words, we essentially need a model of how the observations z are constructed. We're talking about a model of this box that tells us, given a value of x, what are the properties of z. Suppose that instead, however, all that we have in our hands is the distribution of y and the knowledge that x and y are independent. Somehow we need to use this information to find the distribution of z. So let us start working towards this goal. We can figure out what the answer will be quite intuitively. If I tell you that capital X takes a value of little x, then in this conditional universe, z is going to be just this random variable. And this is the same as the random variable capital Y, except that a constant is added to that random variable. So z is going to have the same distribution as y, except that it gets shifted by an amount of little x. So it has the same distribution as y, except that the distribution is shifted. So instead of having an argument z here, we will need to have an argument z minus x. So this corresponds to taking the distribution of y and shifting it by x. Another way to think about why this argument z minus x here is correct, notice that in order for capital Z to be equal to some little z, then capital Y should be equal to z minus x. This is the value of y that makes the sum of x and y turn out to be the same as little z. So intuitively, this is what we would get for the conditional density of z, and then we could just apply this form of the Bayes rule. It's instructive, though, to rederive this relation here in a different and somewhat more formal way. So let us go through one more derivation. This time we will give an argument that relies on CDFs. And here's how it goes. We will first find the cumulative distribution function of z conditioned on x. That is, we will attempt to calculate this conditional probability. And then, since this is a conditional CDF, we will then take derivatives to find the conditional PDF. Now this probability, by definition, z is x plus y. So we have this probability conditioned on x equal to little x. But if we know that capital X takes a value of little x, then this capital X here can be replaced just by little x. And we obtain this probability here. Now, this is an expression which is a random variable because y is random, but little x is a number. So y is the only random variable involved here. Y is independent from x, so the conditional distribution, given the value of capital X, should be the same as the unconditional distribution. And finally, we can rewrite this event in this form. It's the probability of capital Y being less than or equal to z minus x. And we recognize that here we have the cumulative distribution of y, but evaluated at little z minus x. Here we have the cumulative of the conditional distribution of z given x. We take the derivative of this quantity to find the density of the conditional distribution of z given x, and that density has to be equal to the derivative of this side of the equation. And the derivative here with respect to z is just the density of y evaluated at z minus x. So we have verified using a second method that this formula here is correct. So here is a summary of what we have done so far. We basically wrote down the form of the Bayes rule, and we wrote down how the distribution of z can be expressed in terms of the distribution of y. And so we now have available an expression for this term that appears in the numerator. Now let us look at a concrete example. Suppose that x and y are exponential random variables with a common parameter lambda. How are we to think about this situation? We start at time 0, we have a light bulb, we wait until a light bulb burns out, and the time until a light bulb burns out is exponentially distributed with some parameter lambda. Then we start using a new light bulb, and that light bulb will also remain alive for a random amount of time, call it y, and at that time the second light bulb burns out as well. The total amount of time that has elapsed, we call it z. Somebody tells you the value of z. That's when the second light bulb burned out. And you're trying to say as much as you can about the value of x. You know that x, the time of the burnout of the first bulb, was sometime before z, but you do not know where exactly in that interval it's going to be. So what we want to calculate is a probability distribution for x, which is going to be a probability distribution on this interval. So let us now calculate. In this example, we're assuming that x is exponential, so the density of x takes this form for x non-negative. We are also told that y is exponential with the same distribution, so we have the same expression for the density of y. And now we can fix some z non-negative. Only non-negative z's are possible. So we will try to calculate this conditional PDF only for non-negative z's, and using the form of the Bayes rule that we have, what we got is, let's first put down the denominator term. And here we have lambda e to the minus lambda x, and this is valid when x is non-negative. And then we multiply with this conditional density, which is the conditional density of y evaluated at z minus x. And this is going to be lambda e to the minus lambda z minus x. And this expression here is valid when the density of y takes this form when the argument is non-negative. So it takes this form when the argument is non-negative. The argument is z minus x. So this is valid when z minus x is non-negative, or what is the same, it's valid when x is less than or equal to z. So in this range, when x is non-negative and x is less than or equal to z, we have this expression. Now we notice that we have a term e to the minus lambda x here, and we have a similar term here, but with an extra minus sign. So these two terms will cancel each other, and what we're left with is the following expression. And this expression is valid given the constraints that we have imposed so far. Z is non-negative, x is non-negative, and x is less than or equal to z. So it is valid when x and z obey this condition. And this is the form for the conditional PDF of x if I tell you the value of z. This is the form that it takes. What's special about this PDF? Remember that we have fixed z to a certain value, and we're trying to describe the likelihood of the different values of x. But there is no dependence on x here, so the PDF is constant as a function of x. And this means that if I tell you the value of z, then x is going to have a uniform conditional distribution on this interval. And this is quite interesting. Essentially, it tells you the following. Going back to our light bulb example, if I tell you that the second light bulb burned out at this time, and I ask you, when do you think the first light bulb burned out? You're going to tell me, I really don't know, I have complete ignorance. Any time in this interval is in some sense as likely as any other time. Now, this conclusion might seem perhaps surprising or unexpected, but it becomes quite plausible if you start thinking in terms of coin tosses and the geometric distribution. To make a discrete time analogous story, we could think as follows. We have here time that is divided in slots, and you keep tossing a coin until heads is obtained for the first time. And this is a geometric random variable. Then you keep tossing again until heads is obtained for the second time. So this y is also going to be a geometric random variable. If I tell you that the second heads showed up at this time, and I ask you, what do you think about the first heads? Well, you're going to tell me, I know that there was exactly one head in the time up to here, but all slots are equally likely. The one head that we have may have appeared in any one of those previous slots, and each one of those previous slots has the same probability.